Welcome back to Advanced Machine Learning. I'm Ludwig Botmann, and in this video I will introduce you to imbalanced learning. You should know what an imbalanced dataset is. You should understand the disadvantage of using accuracy on imbalanced datasets, and you should know some techniques for handling imbalanced datasets. Imbalanced data means that the ratio of the classes is significantly different. So here we have an example of two Gaussian distributions. We have a positive class and a negative class, and on the left hand side these are equally sized, so we have as many positive observations as we have negative observations. But on the right hand side we have an imbalanced data set, which means that we have just a very small number of positive instances, and most instances are from the negative class. A consequence of this imbalance can be that we have undesirable predictive behavior for the smaller class. Here are some examples where this can happen in real-world use cases. So, for example, in medicine we could have the task of predicting what the tumor is like. So is it a benign or a malign tumor? And the minority class may be the malign tumor class. Or in information retrieval we want to find relevant items, but the minority class are the relevant items. And often the problem is that the important class is the class where we have just a few observations. For example, also in tracking criminals. So, for example, we want to detect fraud emails or other fraud cases, then the fraudulent cases are the minority class, and we have a really vast majority of non-fraud emails or cases. And for weather prediction, for example, if we want to find or to predict some extreme weather scenarios like a tornado or a hurricane, we only have very few amount of days where this happens, and most of the days the weather is kind of normal, whatever that means, but basically not having a tornado or a hurricane in that example. And the problem is that, well, the thing we want to know most about is the minority class. This can also be a source of bias related to the concept of fairness, which we will not treat in this chapter. So we have an issue with evaluating classifiers for imbalanced data. So ideally we want to correctly classify as many instances as possible. Of course, we want to have a high accuracy, preferably we want to correctly classify all our observations, so 100%. So what we obtain in practice on imbalanced data sets is that we have a good performance on the majority class, but a poor performance on the minority class. And the reason is that the classifier is biased towards the majority class, as predicting the majority class pays off in terms of accuracy. If we look at this example here, assume that we have a rare disease. Okay, so just 0.5% of patients or of people have this rare disease. So let's imagine we have a prediction scenario where a new person comes in and we want to predict if this person has a disease or not, or we want to diagnose if the person has a disease or not. So if we just always predict that the patient or the person is healthy, so does not have a disease, then directly we have an accuracy of 99.5%, which sounds great at first hand. But of course it's not, because this classifier did not learn anything about the disease. Okay, and we will overlook all the persons who have the disease, which is of course not what we want. So focusing only on accuracy can lead to bad performance on the minority class. I'd like to visualize this here with a small benchmark study where we have 10,000 observations in the negative class always, and then we have different scenarios for the positive class. So the first scenario is 10,000 observations also the positive class. Then we have a ratio of 1:1. So these are the values on the leftmost side of those four plots. And then the number of positive instances varies and decreases from left to right. Okay, and on the very right hand side we have a very unbalanced data set of 50 positive instances compared to 10,000 negative instances. Okay, then we train our classifier and with tenfold stratified, cross-validation, evaluated on test set regarding different performance evaluation metrics. We have accuracy, true positive rate, so recall, positive predictive value or precision, and the F1 score, which balances the TPR and PPV, so the recall and precision. And what we see is that the accuracy goes up if the imbalance increases. Okay, as we have seen before, if you just predict a negative class always, then this is quite a good classifier in terms of accuracy. But the true positive rate, so the recall on the positive class, so on the smaller class, goes down. So we find less and less of the positive observations if the imbalance increases. This is not as bad for the positive predictive value, the precision. We cannot see a clear trend here, so we also do not have any confidence intervals here, so I wouldn't say that we have a clear trend at all. But with TPR having such a clear trend and with PPV not having a clear trend, then the F1 score, of course, takes up the trend of the TPR, so also goes down for increasing imbalance. And now, of course, the question is, well, what do we do about imbalance? Well, an ideal performance metric would be that the learning is properly based towards the minority class, so we could force the learner to be better on the smaller class. Some imbalance-aware performance metrics are the G-score, the balanced accuracy, Matthews correlation coefficient, and weighted Maker F1 score. And, well, for today I will just name drop them. You will see details later, of course. We can divide approaches in different solution levels, let's say. One level is the algorithm level, where we try to bias the classifier actively towards the minority class. So we try to force the classifier to be better on the minority class. This needs some special knowledge about the classifier, of course. The other approach is to change the data a little bit, so to rebalance classes by resampling, or see oversampling, undersampling, SMOTE, and the good thing is we do not have to modify the classifier at all. Then there is something in between algorithm and data level approach, that's cost-sensitive learning, where we introduce different costs for misclassification during the learning process. So this would mean that false positives and false negatives are not equally bad. Okay, so we would, for example, penalize classifying a positive instance as a negative instance more heavily than the other way around. And then finally we can do some ensemble learning plus one of the three techniques above.